Hello and welcome. In this video, we're going to look at how to calculate series RLC circuits at resonance. So we'll start off with our resonance frequency, which is our FR equation. That always results back to our 1 over 2 pi with all of our time constants. So anytime you see an F variable, you want to look for your 1 over 2 pi equation. So in this case, it's 1 over 2 pi. The 1 on top says I got a frequency. The 2 pi says I'm running that frequency around a circle. And then whatever's at the end of this is going to be your time constant. And in this case, it depends on the circuit. So we have an R, L, and a C in our circuit. So we need to use the square root of LC time constant. Right, so if we just had an RL in there, we would use just the RL time constant. And if we had an RC in there only, we would use the RC time constant. But because we have an L and a C in here, the inductive and the capacitive load, we need to use that time constant for it. So this is our F equation, and it's going to get us our frequency at resonance. Resonance is when the inductive load and the capacitive load match each other. If there's one frequency that happens, anything above or below that frequency will make them unbalanced, and a lot of times we aim at balancing them. So we're going to calculate this out. We'll say that we have all these values here. We need our inductor and our capacitor, which they give us directly. So we'll just type it in, 1 over 2 pi. Square root of our inductor, which is 2.7 millihenries, so 0.0027, multiplied by our really small capacitor value, so 22 times 10 to the pico, that's negative 12. And that gives us a frequency here, a very large frequency. They want it in kilo ohms, so we'll move that decimal point over and just say 653 kilo ohms is our answer. So 653. So at that point, we can figure out what our XL and our XC are because we know our frequency now. We know that our XL and XC variables have their own equations. So XL is equal to 2 pi FL, and XC is equal to 1 over 2 pi FC. We could plug both of those in this out. We'll say that we have 2 pi, start off with our XL equation, multiplied by our frequency, which we just got was 600 and, oh, we didn't multiply, 653,000. We'll just round that off like that. Then we'll also multiply by our really small millihenry value of 0.0027. That gives us 11,000. They want the full number here. We'll just type it in here. 11,077. Round it up to 8 if we wanted to. The second number here is our XC, so we'll do 1 over 2 pi FC. 1 over 2 pi 6530. Oh, we need to multiply that. Multiply 65300 for our thousands. And then we'll also multiply it by our picofarad, so 22 times 10 times 10 to the pico is negative 12. We get the same number. That's what we expected, really. 11078. And so that's exactly what we got for that last one, 11078, 11078. That's what resonance means. The XL and the XC match each other. So if yours don't match, try calculating them again. And then they want us to find the circuit current. That requires something else. It doesn't tell us to actually calculate out our Z variable, but we know that if we plug in Ohm's law, voltage, current, and resistance, we need that resistance to be a Z if we have capacitors and inductors involved. And so we'll solve for current, voltage over resistance. We'll say I is equal to our voltage over resistance. In this case, our resistance is going to be our Z variable, and so we need to find Z first. So we'll say Z is equal to our resistor plus or minus J X total. We know X total is the combination of XL and XC. So we'll write that out. X total equals XL minus XC. We start there. We'll say that we have same, right? They're going to cancel each other out. So we got 0 as our X total, right? Because these two numbers are exactly the same. And so then we just have our resistor left. So Z is equal to a linear resistance of 3,000 plus 0J. So we'll leave that off. That means that we can just calculate out our voltage divided by our resistance, and we know that we have canceled out our XL and our XC, so they actually don't get a voltage drop. The only voltage drop is our main resistor value here. And so we'll just plug that in. We'll say that we have 10 volts divided by 3,000 ohms. 10 divided by 3,000 gives us 3.33 milliamps. We'll plug that in. 3.33 milliamps is already there, which means that we expect the full voltage drop across that resistor. That's what we used up here. We said the voltage drop across the resistor is all of the voltage. And so we expect VR to be 10. Let's check our answer here. And there we go. So let us know if you have any questions.